butterfly's yellow wing that came into my heart and made it swing back and forth on an oak tree. You're as quick as a comet, smooth like the sea. Like a comet's lips, you make me slip, and I'll make you mine with a single kiss. With your sunrise and golden eyes, so how could I resist? Flowers bloom like it's spring in October, and seasons are slower, and all I need to have you closer. Willow leaves, you made me see that life is full of vitamin D, like bamboo shoots and strawberry juice. Your hand in mine, I could never refuse.
Yeah, I just want to also make sure that it's not so dark or like so. Is this visible or too bright? Can you read it? Okay. Well, I guess welcome to Module 3. Thank you everyone for being in class today. I hope the midterm was okay. If you look on the bright side of things, it is almost time for class to end. We have like a couple of lectures, then it's Thanksgiving break, then you have another week, and then you're done. So you're getting very, very close to the end. And we're going to start switching gears again today to move to a third module, which is Module 3, which is going to be probably the most, you're trying to integrate all of the ideas that you've learned over, the past two modules. So I guess today is also election day. Remember to vote. And it's a good day to be starting actually this module, because what we're going to be talking about in this module is a lot of data processing and what to do with data that you've collected. And if you think about it in the context of politics and in terms of, really understanding how to govern large numbers of people, there's a lot of data that you need to think about. Campaigns obviously do this. They try to understand, how can they predict whether voters will vote, how will they vote. And we're going to be talking about least squares in this module, which is kind of one of the most fundamental methods for actually trying to predict things from a set of data. And this is something that forms the basis of basically any kind of machine learning, whether you're using it for predicting something from a biology experiment, whether you're using it for predicting something in the context of the election and large numbers of people, whether you're trying to predict something in the context of, trying to measure the value of a resistor or something like that. So I guess we'll get started. Today we're going to be talking largely about the motivation for this module, which is also the lab that you'll be doing, which is about locationing systems. We'll also talk about inner products and dot products, which is something you've seen before. It's just matrix multiplication of vectors, but just a new name and a new notation, which does nothing else. And we will also be talking about correlation. If we have time, we'll talk about trilateration, but we may or may not have time to get into that. So we're here in Module 3, but I just wanted to spend a couple of minutes to recap how we've gotten here. We started this class, and we hadn't even defined what a matrix was, right? Defining what a matrix is happened in the first week of class. And from there, we're coming now to the end where we're going to be doing quite a bit of sophisticated data processing using these matrices. And modeling 1 was basically all about modeling and, how to think about the physical world. And if you think about it, a lot of the homeworks that you folks did in Module 1 were about, hey, here's some complicated description of a real-world system. Can you take it and mathematize it and put it into a format that an engineer or a computer scientist can actually understand and work with? How can we take something that is not really precisely formulated, but then make it so that you can actually use a lot of linear algebraic or other mathematical techniques on it? How can you actually integrate these things together? And Module 2 went even beyond that. It wasn't no longer just about modeling, but it was actually, how can we actually physically collect this data from the real world, right? How can we extract information? And then once we extract this information, how do we design to achieve a goal? Right? So first we thought about, what is this physical world? How do we even start to think about it? What are the principled ways in which we can think about this? And then we said, now that we have a principled way about thinking about something, can we actually take information from the physical world and, put it into a format that we can start to process it? And the one way that you saw, and the one we've done the most frequently, is actually thinking about information represented, for example, as a voltage, right? The value of the voltage can change what happens. So for those of you who are doing the touch screen lab this week, you've done touch 3A and this is touch 3B. And what you're saying is that, look, depending on the value of this voltage, you can detect whether or not there's a touch, right? Something that is happening in the physical world gets translated into a signal that your computer can actually process. And you went from scratch to build this, right? At the beginning of this, we had not even defined what a resistor is, let alone define what an op-amp is, and an op-amp in negative feedback and an op-amp as a comparator. And at the end, in lab this week, you guys are building your very own current source, which I think is just completely remarkable. And it's not just like, oh, here, build your own current source and just put together these components, but actually being able to derive why this is the correct way to build a current source and why then this can be used to detect touch. How are you converting something in the physical world into this electronic digital signal that then can be processed? Which is what then brings us to Module 3. And Module 3, I think, is pretty exciting. I'm kind of sad that it comes here at this end of the class where we're hitting daylight savings time and, it's a lot of final projects. People are heading on break. Because I think it's super, super, super cool. We're going to be building up basically in this module the fundamentals of how to process and learn from the information we extract. Process the information and learn from it. How many people have heard of this thing called machine learning? So this module is basically going to be building up to the fundamentals, and we're going to be talking about some of the, most powerful and fundamental tools that will keep coming up repeatedly when you start thinking about machine learning. So we're going to build up to this fundamental idea of least squares, and then we'll talk about some iterative algorithms that can be used for prediction and for learning something from a set of data that you have. So the running example that we're going to use throughout Module 3 is going to be a locationing example. And that's what the lab is going to be about. All of you have heard, I'm sure, about GPS, which is global positioning systems, right? How many people have some idea of how GPS actually works? Right? So in this module, we're actually going to dig into deeply of how GPS works at a basic level. So the fundamental idea of GPS is based on having multiple satellites that are actually in orbit around the Earth. And these satellites are at known locations. And what we do when your phone, when you pull out your phone and you bring up, a mapping application, you see this little blue dot that shows you where you are, right? And the computation that is happening to tell you where that blue dot is what we are going to derive in the next few lectures of the class. And what is really happening is that there are signals that are being transmitted from these satellites to your phone. Your phone is the receiving antenna. These satellites are the transmitting antennas. And through the information that is communicated, your phone is actually able to compute its location relative to these satellites. And because you know the locations of the satellites relative to the Earth, you can then locate yourself relative to the Earth. So in the lab, you're going to actually be building not exactly a GPS system. You're going to be building an APS system, where A stands for acoustic. An acoustic positioning system. Because instead of using electromagnetic waves, which is what a GPS system would use, you folks are going to be using acoustic waves. And you're going to be using this to then implement basically the same idea that a GPS system will implement. So how many people know how many GPS satellites there are, actually? I just looked it up yesterday. Yeah? About 500. There's a lot of satellites, but actually about 30 or 31 of them are specifically GPS satellites, and you actually require only 24. I think there's some goal to have 33 operational satellites, but actually, I guess they haven't reached that goal yet. Or there's some maintenance that happens. So if you actually go, I didn't realize this, but if you go to Wikipedia, it tells you like a list of retired satellites and the list of active satellites. So apparently there's satellites that are not even being used, but are still orbiting because they have somehow broken down. But before we start, solving this problem on a global scale and trying to understand GPS really globally, let's think about the 1D locationing problem. So what is the 1D locationing problem? Instead of trying to locate ourselves in 3D space, which is what we would be doing in a GPS system, let's think about trying to locate ourselves in 1D space. So let's say you know that I am somewhere on this line, and we need to locate, let's say, where I am. And let's say, for example, here's maybe the Campanile or my cartoon drawing of it. And let's say I tell you, oh, hey, I'm at some kind of distance D from the Campanile. You know that I'm along this line. Can you then figure out where I am? I see a lot of heads shaking no. Right? What's the problem here? I could be at distance D to the left, or I could be at distance D to the right. Right? This is also another candidate location. If I give you one landmark and I give you one distance, can you figure out where I am exactly? The answer is, well, you can figure out two possible locations where I might be. Right? Thinking back to now, systems of linear equations. Do we have a unique solution? Do we have enough constraints? Do we not have enough constraints? We're going to come back to this again and again. So what would you need to be able to figure out, where I am? Any suggestions? Yeah? Yeah? A second landmark, right? So, great. What's a second landmark we want to use on campus? Soda Hall. Okay. Let's draw Soda Hall. And how far should we be from Soda Hall? We can be, let's call this a distance D1. Then if I tell you that I'm distance D2 from Soda Hall, now with two landmarks, and using the fact that you know that I'm somewhere along this line, we can say exactly where I am, right? This gives us the two constraints. You can rule out the possibility that I would be on the other side of this. Is this clear to everyone? Yeah? Okay. What would happen if Soda Hall was built on top of the Campanile? Would you be able to figure it out? No, you can't have the landmarks coincide, right? Because you would have basically then some kind of redundancy in the information you're getting. But now, what about a 2D locationing system? What if now I told you I'm somewhere in the 2D plane? I didn't tell you that, I'm somewhere on the line, but I'm somewhere on the 2D plane instead. Let's say I tell you that here's, again, let's draw the Campanile. And I'm at distance D1 from the Campanile. So I brought some drawing aids. So let's call this distance D. This is the campanile. And now we said also our second landmark was Soda Hall, right? So what if I drew Soda Hall? Almost a circle. So D1 from the campanile, and let's say distance D2 from Soda. So how many points in the 2D plane are at distance D1 from the campanile? Clearly an infinite number of them, right? I can be anywhere along this circle if I'm in a 2D plane that is distance D1 from the campanile. Is that clear to everyone? Yeah? And if I'm distance D2 from Soda, but I'm somewhere in this 2D plane, I can be anywhere along here. So, again, do I have exactly one position that I can be identified at if I tell you distances from two landmarks in a 2D problem? I need to find basically a third thing, right? I need to find a third landmark and give you a distance from a third landmark, because right now there are two possible choices for my location, right? I can either be here, or I could be here. But what if we said we had a third location? What's the third landmark you want to have? Corey. And now if we were distance D3 from Corey, then if I tell you D1, D2, and D3, and I tell you the locations in the 2D plane of the campanile and Soda and Corey, then you can identify exactly where I am, right? Because you can say, well, this point is distance, some other distance, not equal to D3, some other distance D4 from Corey, so she can't be here, which means that she must be at this particular point. And this is exactly the same principle by which GPS satellites operate. You have a constellation of satellites, and what your cell phone is doing is it's basically computing the distance of the cell phone antenna receiver from each of these different satellites. And what it's saying is that, well, if I'm distance D1 from satellite 1, distance D2 from satellite 2, distance D3 from satellite 3, where must I be? So now you've seen that in one dimension you need two landmarks. In two dimensions you need three landmarks. So for a GPS system, when you're doing this in 3D, how many landmarks are you going to need? 4, right? What's going to happen there if I think about 3D space, and if my landmark is here and I know I'm distance D from this landmark, is my set of points a circle? It's a sphere, right? And then if I have two spheres intersecting, they're going to intersect not in 2 points, but they're going to intersect in an entire circle, right? That's going to be in a plane. Like if I have two balls that intersect like this, there's going to be a whole ring of points that are actually going to be the set of feasible points. And so to then narrow down from that circle to a unique point, I need to use 2 more satellites. So the question, of course, is that, great, if we can somehow figure out what these distances are, it seems like there's a way that we can actually figure out our position. And the question is, how do we do this? And there's really 2 parts to the thing that we have to do to be able to compute this. First thing we have to do is, we have to, figure out the distance to the landmarks. I mean, one thing I could do is I could carry around a tape measure, And every time I go anywhere, I could say, tape one side to the campanile and like drag it around with me. And then go to Corey and tape it there. And that would be one kind of locationing system. I think I've seen it for I guess dogs have leashes. And sometimes you have the little kid leashes too, right? That parents attach them to. It's one way of having a locationing system, but I don't think it would be very fun. You could try to, every time you go somewhere, compute where you are by maybe sending some kind of robot to can you go see how far the campanile is? Then come back and tell me. But might not also be feasible. So we have to come up with a way that we can actually reliably compute distances from each of these different landmarks. Once we do that, we have to figure out how do we combine these distances to understand our location, right? Right now we're doing this visually and we can see how we'll do this, but we actually need to come up with an algorithm that'll do this for us. And that'll be the second part of what we're going to do. And there's actually a third part, which is really important, and which is the question about how do we deal with noise. So this is something that we talked very, very, very little about in Module 1, and a lot of you had a bunch of great questions about, what if our measurement isn't exact? Or what if we have more equations than unknowns? And a lot of you might have remembered that I said, you know what? That's a great question. Just wait for a month. And we'll talk about it in Module 3. And your day is finally here, because in the next 2 weeks, we're going to be spending a lot of time talking about noise. Because when you actually try and do things in the real world, as you've now seen in lab, you get noise, right? You have a calculated value of what you think the voltage should be, for example, in lab. But sometimes there's a little bit of an error because of various kinds of noise. And this is exactly what we're going to be talking about. And so for this part, we're going to try and understand what cross-correlation and correlation is. This is going to be understanding trilateration. And this will be the least squares algorithm. And all of these concepts are going to be building up into concepts that are very, very important as the first algorithms that you will be learning in machine learning. So for those of you who are interested in taking classes like 189, 188, 127, 126, these are all the concepts that are going to kind of lead directly into this. So, with this, I guess, let's get started. And we'll get started with trying to understand part 1. How to figure out distance. So this is something that, is something we've kind of touched upon, not really touched upon, but I want to give you folks a chance to just think about this question. So take a minute, think about the question. If you feel like talking to someone next to you, talk to them. If you really don't want to talk to anyone, I won't force you, but try to be nice and friendly. Make sure that no one is left out. If you see someone who's looking to talk to someone, please try and be friendly. Try and see what you could come up with. How can you figure out this kind of location? And right? You know that we're going to end up using some kind of signaling. GPS uses electromagnetic waves. We're going to be using acoustic waves. How can you use these electronic waves or acoustic waves to actually figure out distance? Take a minute and just brainstorm. Think about it. It's an engineering class. So does anyone have any ideas they want to share? Yeah. It can be a creative idea, sure. You decided to take a what? Okay. Okay. Okay, so for those of you who didn't hear the idea, they're going to take Usain Bolt, they're going to stick a tablet on his back, they're going to press go, he's going to run to the campanile as fast as he can. You know exactly the speed of his running. When he gets there, he presses stop, and then you can compute exactly the distance because you know the time it took and you know the speed at which he runs. I think that's a great idea. Other ideas? We're going to use something very similar to this. Yes? Great. So for those who didn't hear that, you basically use echolocation. You paint the campanile, you bounce a sound pulse out towards it, and you measure the time it takes to go there and back. And we're actually going to be using something very, very similar to this idea. Any other ideas? I saw another hand. Yeah? Mm-hmm. Yep, so he's pointing out another idea that we're going to be using is have a periodic flashing light and then think about the delay between the light flash and when you receive it, and then you can use this to estimate the distance you're away. Yeah, these are all really great and creative ideas. Okay, anyone else with an idea they really want to share? Okay. So, the idea we're going to talk about in class is not quite as fun as this, but, we can actually build it. So, we're going to use basically a combination of all of the ideas that were brought up, that were brought up just here. And we're going to think about these satellites, and what they're going to do is they're going to send out signals. And what's going to happen is that the receiver, which is me with my little phone, is going to receive these signals. And we know that, both electromagnetic waves and light waves travel at a certain speed. So if we were using an electromagnetic wave, it would travel at the speed of light. So EM would be 3 times 10 to the 8 meters per second. A sound wave, I think it's approximately 340 meters per second. I don't know how fast Usain Bolt runs. But you could also use that, right? You could just send from the satellite, you could send a runner. And now you use the basic idea that the time it takes for your signal to arrive from when it was sent is going to be directly proportional to the distance between you and the landmark, right? This is something that we know. And what do you need, really? There's one fundamental assumption that a lot of people were making in their suggestions here, which is you somehow need to have a synchronized clock, right? When you need to know whether you're using the flashing light, you need to know what time the campanile sends the flashing light, or you need to know what time, the runner starts and the runner leaves. And so you need to have some kind of synchronized clock. between the transmitter. So I'm just going to abbreviate transmitter as TX and receiver, just so I don't have to write the words out. So let's start to, understand this, and we'll understand it in the usual way we do things in 16, which we will start with a simple case, and then we will build up to something that's slightly more complicated. So let's think about a particular signal that is going to be sent, and just like the flashing light suggestion that was made, we're actually going to think about using a periodic signal. So let's say that I'll leave this here. So let's say that the transmitter sends out a signal or a song or something, and it's a series of pulses, right? So let's say we have time 0, time 1, time 2, time 3, time 4. And let's say the song it sends out is the following. 1, 2, 3, 4. So it sends out something like a flashing light. It sends out some kind of beacon, some kind of indicator. It's the pattern. It sends out, and you know that at time 0, it is going to be sending this pulse of size 1. Now, depending on whether you're using an electromagnetic wave or an acoustic wave or some other kind of communication, you will actually, compute, you will actually use, send this in different ways. Like if you're using sound, you might use the volume. If you're using an electromagnetic wave, you might use the actual, like you can use the voltage, for example. You might use, on and off levels for it. There's many different ways in which you can do this. And for now, we'll just kind of abstract this away and think about sending just these values. And we're going to think about this as being sent periodically. So then, let's say if this had a period of 4, what do we want to send out again at time 4? We will send out again a 1. And at time 5, we will send out a 2. And so on. And what about backwards in time? Can we think about negative time as just the time before the current time? Just so that we can have some kind of pattern and we don't have to think about, we can think about things basically in both directions in time. So if 0 is our reference time, negative 1 is the time 1 unit right before that. So what would be here? This would be 4. And this would be 3. And so on. Right? So let's say this is the signal that is being transmitted. And this is what we call a signal. We're going to represent it as x of n, where n is the time index, and x of n represents the value. So here we have, for example, x of 0 is equal to 1, and x of 1 is equal to 2, and x of 2 is equal to 3, and so on. And x of 3 is equal to 4. And is there a more compact way we can write this? Is it just for these 4 values? If I wanted to represent the signal, do I have to keep writing every single value for every single integer number? It's going to be quite painful, right? So I can write this in the more compact way, and I'm going to write x of n is equal to 1 if n is equal to 4 times k for some integer k. Right? So if k is 0, n is equal to 0. If k is 1, n is equal to 4. You can see 0, 4, both have exactly the value 1. x of n is equal to 2 if n is equal to 4k plus 1. X of n is equal to 3 if n is equal to 4k plus 2. And x of n is equal to 4 if n is equal to 4k plus 3. Right? And by this compact writing, I can actually represent an infinite number of samples of this signal, right? Sometimes I'll use the word sample of a signal, and by that I'll mean like one, like the signal value at time 0, or the signal value at time 1. So we can represent all of the values of this signal using this rather compact way of writing. Okay, so we have this, and now let's think about what we receive. So here's the receiver. We have 0, 1, 2, 3, 4, minus 1, minus 2, minus 3. And let's say we receive the following. And let me just draw this here. Okay. So here, we were looking at, this time period from 0 to 3. And we had this sequence, this song that was being sent by the signal, the song, whatever that was being sent by the transmitter was 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And remember, we both have the same clock, but what is the receiver receiving at time 0? The receiver is receiving a slightly different song, right? It's receiving the song 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So it's shifted. And when you can see the shift, what is the shift that you can actually see here? How much is it shifted by? It's shifted forward, right? So instead of receiving the 1 at time 0, I'm receiving it at time 2. Right? So it's shifted, it's offset by 2. So if I think about this part of the signal, 2, 3, 4, 5, it's exactly the same as 0, 1, 2, 3. So if you look at this, what could you conclude about the delay between that it took between the transmitter and the receiver? Okay, this is important. Like, if you're confused, ask me questions. 2 time steps, right? Because the thing that was sent at 0, it's received at 2. The thing that's sent at 1 is received at 3. Yeah, question. Excellent question, right? The question is, since it's periodic, how do you know that it was 2 time steps? Maybe it was 6 time steps, right? Maybe this 1 is not the one that's coming from 0, but it's actually the one that's coming from way over here. And the answer is, actually, I don't know whether it was 6 time steps or not. It could have been 6 time steps. What else could it have been? It could have been negative 2 time steps, right? It can't really in a physical system, but it could have been negative 2 time steps. It could have been any shift that actually is of the 4k plus 2 type, right? I heard someone say that. And so this is something that actually we're not going to be able to disambiguate. But thankfully, because we are the engineers that get to design our locationing system, we will actually be able to design it so that we're not going to run into this issue. In fact, what you will do in the lab is that you will design a periodic signal that is so long that the time it takes, the maximum shift that you're going to get because of the distance is always going to be shorter than the period of the signal. So in a GPS system, the codes that you use, the periodic signals that you use, are actually very, very long. So for example, in this setup, if I told you that, hey, your maximum delay can be 3, then can you tell me exactly what the shift was? What the delay was? Right, but if I don't tell you that extra piece of information, you actually cannot disambiguate. That's exactly the question I was hoping someone would ask. Is everyone clear on that? Yeah, question. The question is, how do you handle really long patterns? And the fact of the matter is that because electromagnetic waves travel so fast, and even in the lab, sound waves actually travel so fast, you can actually have very long patterns and still disambiguate at a very, very fine resolution. So it's not a problem. But good question. Okay, so now, let's say we receive this signal, yn, and let's write yn also in this notation, right? So yn is equal to 1. For what values of n is yn equal to 1 now? Yn is this guy. Is it 4k? It's more like yn is equal to 1 at 2 and minus 2, and so what types of values is yn equal to 1? At what kinds of values is yn equal to 1? 4k plus 2, right? And yn is equal to 2 if n is equal to 4k plus 3. Yn is equal to 3 if n is equal to, what should I write? 4k plus? Just 4k, right? 4k plus 4 is just 4k. Because I can, anything that's 4k plus 4 is also just a 4k. It's just a multiple of 4. And yn is equal to 4 if n is equal to 4k plus 1. Okay. So more generally, can we think about this as, let's say I have some transmitted signal. Let's call it Sn. And let's say it has period n. What are the shifts that you can disambiguate if you have period n? Right? You have to have... What are the possible shifts, first of all? What are the possible shifts that you can even get? You can have a shift of 0. You can have a shift of 1. And you can have a shift of, what's the largest shift you can see? n minus 1. Right? And a shift of n is, again, just the same as a shift of 0. Because you're going to repeat every n samples. So you can have these possible shifts. And we want to figure out, well, is the shift 0 or 1 or 2 or, d? Whatever is, let's say the delay is d. We want to find out what is d. This is our unknown. And our received signal, let's call it r of n. Oh, right, sorry. I wanted to also write out Sn as a vector. So let's write out S as this vector. And what I'm going to do is I'm going to just say, let me stack up all of the values from one period. So if I stack up S of 0, S of 1, all the way up to S of n minus 1, this is a vector of length n that represents one period of the signal, right? And now I want to think about my received signal, which is r of n, and I want to write it also as a vector. R, which is the signal value at time 0, time 1, all the way at time n minus 1. And let's say I tell you that there was a shift of 2, right? There was a delay of 2 between Sn and Rn. Where is this first S0 going to show up? Is it going to show up at time 0? No, right? Is it going to show up at time 1? When's it going to show up? Time 2, right? If the delay is 2, if the shift is 2, S0 will show up at time 2. What if the delay is D? When will S0 show up? At the dth component, the dth row of this vector, right? So this, if my delay is D, is going to be S0. And then here you're going to have Sn. This is going to be dth position. And here you'll have Sn minus D minus 1. And then here you'll have Sn minus D. And our goal is to find D. Yes, question. Oh, perfect. Thank you very much. The question was, should this be Sn or Sn minus 1? And you're right, this should be Sn minus 1. Right? Our last sample, our signal goes from 0 to n minus 1. That's a total of n numbers. Thank you. Okay, everyone clear on this? So what do we want to do? So now we're thinking about basically the shifted vector. And remember, when we shift this vector, what's happening? This stuff at the bottom is just filling in from the top, right? Because of this periodicity. We have this kind of cyclic nature. And so if we want to think about different shifts of this, we want to think about, well, where is this shifted thing going to be? I can think about, let's call Sk is equal to shifted version of S by K. So this means that basically S0 is at position K. So here, what is this guy equal to? This guy is equal to SD, right? And so I want to compare these various SKs, which are the shifted versions of my original signal, to my received signal, and I want to say which of these are the most similar. Because then that will tell me, well, what is the actual shift? What is the delay that I'm experiencing? Any questions on this? We're good? Okay. So that's where we're at. And we want to basically compare two vectors, right? We have this received vector R, and we have actually not just one vector, but we have a set of vectors, Sk, and we want to see which one is closest to R. We want to see how far apart are they. And so what we're going to look at is actually the difference between these vectors, R minus Sk, right? And that's represented by this vector that goes like this. Right? This is the difference between these vectors. This is the vector E. And basically, what do we know? The smaller E is, this means that, closer Sk is to R. Right? So one thing we could do is we could keep subtracting all of these vectors. We could take all the shifts and subtract them from R. and then see which one is the one that's actually closest. Right? That's one way of actually solving this problem. We're going to think about something that's very related, but a slightly faster way to do it, and something that is going to actually be robust to noise and robust to doing this in the presence of actually multiple beacons. So one way, if you only have one beacon and one receiver, you can do the subtraction trick. We're going to actually think about a slightly different way to do it. But before we actually fully get to that, I want to just do a little bit of a reminder. On what is the dot product? Or another word for it is just inner product. We've seen this in module 1. Let's say x is a vector, and I take its transpose, and I have y. So I have basically something that's like this, a row times a column, right? What do I get out? Let's say this is x, comma y belong to Rn. What is x transpose times y? It's a scalar, right? What is the dimension of it? It's just going to be 1 by 1. And this operation is called the dot product or the inner product of x and y. There's nothing fancy about it. You've done it many, many times before. It's just another name. So x transpose y, which is sometimes written as x dot y, but it's kind of a tricky notation that we try to avoid using, and I recommend strongly that you avoid using as well because these dots are hard to see. And so a better notation is x inner product y. And we write these triangle brackets to indicate the inner product or the dot product of these two vectors. But really all this is it's x transpose y. Nothing fancy, nothing new, something you've seen many, many times before. But we're going to actually use the inner product or the dot product to be able to figure out this distance business. So for this, let's now come back here. Can you see this? Yeah, okay, good, you can see this. And I will remove that paper. And I will call this page 5. Okay. So here, I'm going to call this guy our S, the one in the red box, and our received guy is this guy in the purple box. Is it okay if the top of that gets cut off so that I can have this paper here? Can people still make out what I'm doing? Okay. So I'm going to write S is equal to 1, 2, 3, 4, which is equal to S0, S1, S2, S3. And I'm going to write this as equal to S of 0, because this is basically S shifted by 0. Now if I wanted to write out S1, what is S1? If I have S1, where does the first value start? Not at position 1, it starts at position... Everyone's asleep. 2. And then I wrap back around, and I get back up 4 at the top, right? And then what is S2? It's 3, 4, 1, 2. And S3 is equal to 1, 2, 3, 4. Everyone see what I did here? Nothing complicated, right? Just shifting. And what is my R? My received vector is 3, 4, 1, 2, right? So let's compute some values. Let's compute S naught transpose times R. S naught transpose times R. So this is just the dot product. So how many people remember how to do the dot product? Okay. Just for memory's sake, like, take a minute and compute this. You can talk. So, what do you do here? You take 1 times 3 plus 2 times 4 plus 3 times 1 plus 2 times 4, right? Dot product of two vectors. What do you get out? 24. Okay. What? Oh, sorry. What do you get out? 22, sorry. Okay, good. What about S1 transpose times R? Now you can't trust me to do the math. You have to do it. This is basically 12 plus 4 plus 2 plus 6, and it is 24. S2 transpose times R. What is this? This one's easy. This is 3 squared plus 4 squared plus 1 squared plus 2 squared is S3 transpose times R is equal to 4 plus 2. Did I do the math right? So, in this case, we can cheat a little. What do we know is the right answer? What is the shift? 2, right? So, is there something we notice about the dot product for the shift of 2 compared to the others? What? It's bigger, right? It's the largest one. And the question is this coincidence, or can we use this trick repeatedly? And for this, we want to introduce an idea of correlation. And once we do that, then we're actually going to understand why this trick works. We're going to prove that it works, not just believe that it works. But remember, we have this definition for the dot product, right? Everyone remember the definition of dot product? And remember, we can write this basically as the sum of I going from 1 to n of, let's say, x of I times y of I, right? This is all the dot product is doing. We can write it in this notation if we're thinking about the elements of the vector as the samples of our signal. Now, we define the cross correlation of x and y which are periodic with period n, which is just, it's basically a shifted dot product. And this correlation for these signals of period n, x and y, the order here is important. We'll come more to this in the subsequent lectures. This I'm going to define to be equal to I going from 0 to n minus 1, x of I, y. Correlation sample. Okay. So the correlation of x and y is also something you compute at different shifts, and you get out a vector. It is of length n, and what you see is that we define this as basically take one of the signals, take the second signal here, shift it by k, right? So here, if we think about the shift of 2, if I take 0, 1, 2, 3, and I shift it by 2, so y of I minus k, so what is that going to do? It's going to say if k is equal to 2, it's going to take exactly this value at 0 and put it at 2. And it's take the value at 1 and put it at 3. And it's going to take the value at 2 and put it at 5. So all we're saying is we're mathematizing the shifting operation. And then we're taking the dot product. So really we're doing nothing other than shifting back and forth and doing the dot product, which is something we've done a lot of already. And just to match this up, let's look at some correlations, right? So let's look at the correlation of R and S, and the period of this is 4, and the 0th sample of this. So let's say this is equal to, just plugging into the definition, going from I equal to 0 to 3, R of I times S of I. Right? I just plug this into here. What do I get out? R of I times S of I for I equal to 0 is exactly this times this, this times this, this times this, this times this, right? Which is exactly what I had here. I have 3 plus 8 plus 3 plus 8, which is not equal to 24, but is equal to 22. Okay, what about the correlation of R and S at shift 1? R of I, S of I minus 1. So this is equal to R of 0 times S of minus 1 plus R of 1 times S of 0 plus R of 2 times S of 1 plus R of 3 times S of 2. So what is this S of minus 1? I can think of S of minus 1 exactly as S of 3, right? Because it's, again, remember, our definition is of this form, right? So minus 1 is 4 times minus 1 plus 3. So anything, like I can choose any value of this form and repeat this. So this is basically, again, I can have this just be equal exactly to S of 3. And so now if I look at this one shifted S1 transpose times R right here, what is this exactly equal to? Is this equal to 12 plus 4 plus 2 plus 6? Right? I have 4 times 3. Remember, this is just S of 3. So now this is exactly this. S of 3, S of 0, S of 1, S of 2. So I have exactly this, which is exactly 24. So do I need to do out the other 2 cases, or do you get the pattern? Right? This correlation is basically giving us a way of doing the shifted dot product over and over again quite easily. And actually, there is quite a nice way of thinking about this in terms of matrix vector multiplication. So now, what am I really doing here, right? I have this. But what I'm really doing is I'm taking this vector S and I'm shifting it, right? I have S of 0, S of 1, S of 2, S of 3. And I'm taking the dot product of this vector with this vector R of 0, R of 1, R of 2, R of 3. But I'm doing this now for these different shifts. So I have, this is the shifted at 0. This is the 0 shifted version times R. But if now I wanted to put something here that would give me the 1 shifted version so that I could fill out this matrix, and instead of having to do these stacks of vector-vector products, I could just do 1 matrix vector multiplication, wouldn't my life be much easier? So what would you want to write in this second row? So if I wanted to shift things, yeah. I would take exactly the shifted version, right? I'm taking this times this. Here I'm just writing this transposed, right? I'm just taking and transposing this because the dot product, the first vector we always transpose. So I'm writing it, instead of writing it as a column, I'm writing it as a row. Exactly what he said. So I'm going to have S of 3, S of 0, S of 1, S of 2. And now I'll have again S of 0 shifted again 1 by 1 more, S of 0, S of 1, S of 2, S of 3. And my last one is shifted by 3, right? N minus 1 is 3, because n is 4. S of 3, S of 0, S of 1, S of 2, 0. And this, what I get out here, is the correlation between S at all of these different shifts and R. This kind of shifted matrix has a special name. It's called a circulant matrix. Yeah. Great question, great question. So for those that didn't hear, does it matter which direction you shift it? You can kind of think of the second row and the last row as both shifts of 1. Excellent question. And it does matter, and we're just setting up a convention of shifting forward. So when I say a shift of +1, I mean that this sample at 0 moves to the sample at 1. Here I'm thinking of a shift of +2, so the sample at 0 moved to 2. But, to answer your question, because this period is 4, a shift of +3 is also equal to a shift of -1. So we're setting up this particular convention. You could set up another algebra where you're defining everything as the negative. But there's a standard convention. And the nice thing is that you guys are the engineers. If you really wanted to do things in the opposite way, you could. Everything would turn out to be exactly the same. But great question. So in our case, because our period is 4, minus 1 is equal to plus 3, plus 1 is equal to minus 3, and plus 2 and minus 2 are actually exactly the same. That's how this example particularly worked out. But if you had a period of 5, plus 2 would not be equal to minus 2. Yeah. What does the correlation tell us? We're getting right there. So the correlation is basically measuring a similarity matrix. It's a similarity metric between these two things, right? What did we see here? Why did we even start going into correlation? We started going into correlation because we noticed that when we consider these different shifts, the right shift actually had this highest value. And what we're going to see is that actually a higher correlation means that these vectors are closer together. So with that, let me just finish up answering exactly this question, is what is the correlation? So remember, we wanted to compare this vector r with sk, which are these different shifts, right? And we defined E, which is equal to r minus sk. And we wanted to find the smallest E. We wanted to find the E with the smallest length. So we wanted to minimize the length of E. But what is something that we have learned that tells us the length of a vector? Remember what a norm is? This tells you how long a vector is, right? So a norm is basically a measurement of how long the vector is. If you have, let's say if you have E was 2-dimensional, then the norm of E would be equal to square root of E1 squared plus E2 squared. This is called the Euclidean norm or the 2 norm. You can define other kinds of norms, but in this class, largely we're going to be thinking about squaring and taking a square root. And you can also think about the squared norm, which is just removing the square root, because square roots can be annoying, and just thinking about it this way. And if you remember, we saw another way of thinking about this, right? This is basically just the dot product of E with itself. Right? This is just E transpose E, which is equal to E. But we want to minimize the length of this guy, so we want to make it as small as we possibly can. Why? We want to we want to make R and S be as R and SK. We want to find that SK that is closest to R. So we want to find an E that is as small as possible, right? We want to make sure that this norm of E is small. A small norm of E means SK and R are close to each other. Let's draw that picture again. And this was our E. So we have the length of E squared, which is, this is going to be exactly equal to this. So now E, we know we can write it as, we defined it this way, R minus SK, right? So we can write this now as R minus SK transpose times R minus SK. Right? I'm just substituting this into here. Now I can use the distributive law to write this as R transpose R plus SK transpose SK and then minus SK transpose R plus R transpose SK. I did nothing but algebra here, right? What can we write this as? This is basically the norm squared of R. This is the norm squared of SK. And then minus these guys. So remember that there's a negative sign here. There's a negative sign here, and we want to minimize this length. So if I want to make this small, and there's something with a negative sign here, what do I want to do to make this small? I want to make this thing with the negative sign, I want to make it big, right? So let's think about these guys. So SK transpose R is just the dot product of SK and R, right? And what about R transpose times SK? When I think about dot product, X transpose Y, this I can also write as Y transpose times X, right? Because here you can see from this definition that it doesn't matter if you have Y transpose times X or X transpose times Y. So actually both of these terms turn out to be equal exactly to SK R, and I can just write this as 2 times this. So now, finally, remember, I want to find a K to minimize this length of E. Does the length of R, does the norm of R depend on K? Nope. Does the norm of SK depend on K? SK is just the shift, right? And the norm of S is just the sum of the squares of the elements. Regardless of how they're ordered, SK, this is always equal to the norm of S. So this doesn't depend on K. So only the inner product, only the dot product of SK and R is what matters. And we want to make now the length of E small, which means we want to make the inner product between SK and R big. And what was correlation doing? Right? What did we find here? We tried to find the biggest dot product. So this is why correlation matters. This is why we're trying to find the correlation, and this is why making the correlation big means making the error or the difference between SK and R small. So you'll see more about this in discussion, and we'll pick up from here on Thursday. Thanks.